Hello, of course I'm not Laura Batlle, but she's now in a 1 month stage in the Netherlands, so I'll do the presentation. It's nice to be here and to see you, colleagues, friends and students in person. So this communication is about the role of how to detect and monitorize somatic variants, in this case in autoimmune lymphoproliferative syndrome, or ALPS. And ALPS is a good model to understand the importance of apoptosis in lymphocyte homeostasis. So there are two main pathways of apoptosis. The intrinsic one, which relies in the balance between pro-apoptotic or anti-apoptotic proteins of the BCL2 family, and it starts with the permeabilization of mitochondrial membrane and then all the executionary spaces. And then the extrinsic pathway, in which the most well-known receptor is the FAS and FAS ligand interaction, that through this FAT-associated domain protein also initiates the caspase apoptosis. So in ALPS, the extrinsic pathway doesn't work properly, and this illustrates the important role of this extrinsic pathway in the elimination of autoimmune lymphocytes, because the main manifestations of ALPS are autoimmune manifestations. So these are the clinical criteria. This is the last update about published by the European Society for Immunodeficiencies, and you can see splenomegaly, lymphadenopathy, autoimmune cytopenias as the main clinical manifestations, and then there are other laboratory markers, and typically are accumulation of CD3 positive, TCR, alpha beta positive, CD4 and CD8 negative T cells. So to make it simple, these are conventional lymphocytes, but they are double negative, so we call double negative T cells. And these patients, due to these autoimmune manifestations, are treated with immunosuppressive drug, mainly sirolimus, as a first line of treatment. So regarding the genetics are quite simple and complex at the same time. Are simple because most of the patients display mutations in FAS, which is the receptor, and a few patients display mutations in FAS ligand or in caspase 10, although caspase 10 mutations are quite controversial. But inside FAS, genetics are more complicated. Here you can see FAS is a member of tumor necrosis factor superfamily, like TACI or BAF receptor, as Andrea showed us before, and acts using homotrimers, and these homotrimers interact with FAS ligand and then form this disc that initiates the apoptosis activation and caspase activation and apoptosis. So most of the patients display germline heterozygous mutations in FAS, and the majority of them, of these mutations, are located in the intercellular part of the FAS, and these mutant forms can be introduced in these homotrimers in a dominant negative effect, meaning that these homotrimers, if only one mutant form is introduced, the trimer is not working. So although the patients have half of the proteins wild type and half of mutant, most of these trimers do not work because, as I said, only one mutant form incorporated in this homotrimer, makes this trimer non-functional, okay? So about 75 or 80% of the patients have these heterozygous dominant negative mutations, and the other quarter of patients had germinal heterozygous mutations that provoke mutant forms that are not incorporated in the homotrimer or are not produced because are truncated forms. So in this case, the mechanism is haploinsufficiency, and these patients has substantially less clinical penetrance because these patients have half of the protein, so they cannot form so much homotrimers, but the homotrimers form are all with wild type proteins, so they can work, okay? So the clinical penetrance is low. There are few patients with homozygous mutations in FAS. This display a severe early onset disease. And these heterozygous haploinsufficiency patients that display clinical phenotype, it is thought that there are secondary hits that can contribute to this clinical. So the germline mutation was the first hit. And then other hits about that can be somatic loss of heterozygosity, germline second hit, or other hits in gene related with the pathway can contribute to the clinical manifestations. And the second most common cause of ALPS is somatic mutations in FAS. So not germline, but somatic. You know that somatic mutations arose after zygote formation during embryogenesis or during postnatal life. And these somatic mutations account up to 50% of ALPS cases. Most of these mutations, almost all, are intracellularly in the death domain or other intercellular parts of the protein. So the mechanism is a dominant negative mechanism with high clinical penetrance. And these somatic variants are principally detected in these double negative T cells which are elevated in this patient. So the classical approach to detect these mutations is to isolate these double negative T cells by cell sorting and then to perform Sanger sequencing of these of these cells. So in this study, we wanted to solve some of the questions that we were interested in. That is about the evolution of these FAS mutations over time in the patients. If this evolution is influenced by the treatment, and if these mutations can be identified even in patients under the treatment. So this story begins with this patient, which is 11-month-old patient with, different characteristics that makes it highly suspicious for ALPS, splenomegaly, autoimmune cytopenias, hypergammaglobulinemia, and especially these elevated double negative T cells. So we studied this patient 6 or 7 years ago, and first we did Sanger sequencing of FAS and Caspase-8 and Caspase-10 without finding any mutation. And as I told you, somatic FAS variants are the second common cause of this disease. At that time, the classical gold standard approach, which is to do cell sorting and FAS sequencing, the cell sorting was not available for different reasons. And we tried an alternative approach that was isolate CD3 positive cells by a simple magnetic system. Because double negative T cells are inside these CD3 positive cells. So we enrich, not purify, but enrich this population. And we try to do Sanger sequencing. You can see here that in total blood, we could not detect any possible variant, but in CD3 positive cells, you can see this small pattern of double peaks that indeed correspond to a pathogenic mutation, pathogenic somatic mutation, consisting in a 4 nucleotide insertion in the exon 9, which is intercellular part where all or most of the somatic variants are located. So I have a disclosure here. We were lucky to do this, to identify this mutation, because this mutation is a frame shift mutation and you can easily identify this pattern. If you imagine a point mutation, single point mutation, for example, like this one, it could be difficult. So do not try at home or at lab, but we were lucky in this case. So what we did is to solve this question is to collect, to do a follow-up of this patient during 5 years. And we collected 6 different samples during these 5 years. You can see it in this table. The 2 first samples were at the initial stage without treatment, so with elevated double negative T cells. And the 4 remaining samples were obtained when the patient was under sirolimus treatment. And you can see here that the sirolimus restored the normal numbers of double negative T cells. With all these 6 samples, we did a technique called deep amplicon sequencing that consists in amplification of the exon of the variant by PCR, and then do next generation sequencing at high coverage to try to detect the variant. And here are the results. These are the 6 samples that we obtained. In blue, you see the percentage of double negative T cells elevated before the treatment and normalized after the treatment. And we were able to identify the somatic variant in all 6 samples. This is the BAF, which means variant allele frequency, so the frequency of the variant in each sample. And you see a nice correlation between the BAF and the double negative T cells. So here, I want to highlight some messages. First, we have been able to detect the variant even in samples after 4 years of treatment with very low numbers of double negative T cells, in fact, normal numbers of negative T cells. So the mutations is still there. All the cells are in normal numbers. And we use this NGS approach with high coverage, meaning that at the position of the mutation, we have at least 20,000 reads to identify this variant. So we are able to identify the variant in patients under treatment. However, I have to say again that in this case, we had the advantage that we know the specific variant. And we wanted to know if it is possible in a discovery setting when you don't know the exact variant that you want to find. So to that, we use this last sample, which has normal numbers of negative T cells. And in this last sample, we obtained total blood, and we did also this CD3 enrichment. We amplified the exon 9, and we used a software to identify somatic variants without telling the software that the somatic variant was there. So this graphic means this is the chromosomal location of exon 9 of FAS. This is the variant allele frequency, and each point is a variant, is a potential somatic variant identified by the software. The true variant is this one, marked by an arrow. So the message is this software identifies many potential variants, more than 400, both in total blood and in CD3 T cells. 99.9% of these variants are non-real variants because NGS produce a lot of noise and background. But you can see that our variant has a slight more frequent BAF, variant allele frequency in blood, and especially in CD3 positive cells. So a simple CD3 enrichment step may be useful to detect these somatic variants by NGS in blood of patients under treatment, which is a thing that, or is an approach that has not been tried before. So the take-home messages of this study, which has published just 10 days ago, is that do not use Sanger sequencing on CD3 enriched cells. We were lucky in this case. But you can do deep amplicon sequencing in total blood to detect these fast somatic variants. And what we propose when you have a diagnostic of ALPS suspicion, the workflow should be first to do a targeted gene panel covering germinal mutations in FAS or other less frequent genes, which are the most common cause. Then you can do, you can try to detect somatic variants in the panel data. Maybe it's not the ideal situation, but it works sometimes. But then you can do, if you do not detect mutations with these two strategies, you can do this deep amplicon sequencing that can work in patients even under immunosuppressive treatment. So I would like to thank Laura Valle, who is the first author of the study, and all my colleagues of Vall d'Hebron from the lab and from the clinical part, and thank you very much.
Some question, and the last question.
Thank you, Roger. Very interesting. No, it's just a very punctual question. Why do you stress that it's under an immune suppressive treatment? Because you will have less cells, or what? Because how do you expect that the immune suppressive treatment is going to affect the detection of these mutations?
Yeah, because this somatic variant is mainly in these double negative T cells, which are elevated at the time of diagnosis, and the sirolimus or immunosuppressive treatment reduce these double negative T cells at the normal levels. So the patient in those last samples had normal levels of double negative T cells, and the message is that although the numbers are normal, the mutation is there at low levels, but it's detectable.
One more. And the last.
Nice talk, Roger. Did you try this informatic method in patients with unique mutation? Because maybe I'm not in deep with the software, but maybe this pattern changed across the exon can give more information to the software to say there's something wrong, and maybe trying with a unique position mutation?
We didn't try it. This software is called BarScan2. It's available, freely available. And we did not try, so our plan is to apply this method to patients with ALPS suspicion, but without genetic diagnosis. And answering your question, I think that in this case, point mutations or these insertions or deletions that produce frameshift will be equally found by the software, because the software analyzes individual reads and detect each variant. So it applies several quality criteria, but at the end, if the mutation is real, you can expect a little bit more of BAF, the variable frequency, or at least a little bit more quality control.
Well, thank you very much.